Hello, today we are going to start our discussion of Chapter 4. So Chapter 4 deals with atomic theory and elements. Now specifically in today's video, we're going to be talking about the history and development of atomic theory and the periodic table. So the first portion here, we're going to take a pretty quick history through the development of what we're going to refer to as atomic theory, or our modern visualization of the atom. So, if we look back to the ancient Greeks about 2,200 years ago, 400 BC, where we first see mention of this concept, right? And here you have an ancient Greek scholar, Democritus, using the term atomos to think about stuff, right? To think about how stuff exists. So at the time, there was this sort of battle going on between one school of thought, which thought the same way Democritus did, that matter was particulate, right? That it was made up of smaller units. And another school of thought, proposed by people such as Aristotle and stuff, that believed that matter was more what you might think of as continuous, right? That, that it was just what it was. It was just one solid thing. There was no smaller sort of identifiable pieces of that matter. And so Democritus gave us this, or introduced this term atomos, which meant indivisible, because he thought that matter was made up of these ultimately indivisible, indestructible pieces, right? Now, this idea was largely ignored and largely forgotten because Aristotle's school of thought about continuous matter is the one that won the day in terms of what most people ended up believing. Now, it wasn't until about 2,200 years later when we get to the first what we think about in terms of atomic theory, right? And this is when Dalton proposes his first atomic theory. Now, of course, Dalton didn't just come up with his theory out of the blue. It's the culmination of a couple hundred years of sort of scientific thought and experimentation, which we commonly refer to as the scientific revolution, which begins in 1600s, around that time. So, remember, when we use the term atom, we've seen this term now a couple different times, we think of atoms as these submicroscopic, very small particles that are the fundamental building block of matter and the smallest identifiable unit of what we refer to as an element. So, all of this sort of ideas are first put into some coherent, theory, right, by John Dalton, right, in 1808, and his atomic theory, depending on which source you read, has 3, 4, 5 parts to it, but I'm just going to go with, what your textbook is going to think about, and it divides into 3 basic points. And the first part is each element is composed of tiny indestructible particles called atoms. Now, it is not surprising that this term is used, right? Scientists of the day would have been familiar with Democritus's ideas and the use of the term atomos. And so this use of the term atoms is not surprising to describe these tiny indestructible particles that are part of Dalton's theory. He goes on to further state that all atoms of a given element have the same mass and other properties. So in other words, all atoms of a given element are the same, according to Dalton. And that distinguishes them from atoms of other elements. So, to summarize this second point, right, all atoms of a given element are the same, but they are somehow different from the atoms of a different element. So, while all carbon atoms are the same as every other carbon atom, they are fundamentally different than an iron atom. Now, at this point, nobody knows what that difference exactly is. But we know they are different. And lastly, atoms combine in simple whole number ratios to form compounds, right? So this idea that, carbon and oxygen combine to form compounds like CO2, right, in a 1-to-2 ratio, and CO in a 1-to-1 ratio, right? So this is the idea of what he's getting at here. Now, this is our first look at a theory, right? And as we see here, this theory is a combination of different hypotheses, right? So the fact that each element is composed of tiny indestructibles called atoms, that's a hypothesis, right? Now, it has become a very well-established hypothesis, but it is just a hypothesis, right? Dalton couldn't see them. He didn't have any idea that they were. It was his idea. And the same thing, all atoms of a given element are the same, right? Another hypothesis, supported by experimental data of the time. And atoms combine in simple whole number ratios to form compounds. Again, another hypothesis supported by experimental results that had been observed by Dalton and others leading up to this point. Right? So he's combining these several supported hypotheses to come up with a theory to try to explain some bigger picture, right? To explain why atoms are the way they are, or what are they? How do they exist? So, 1808, we have Dalton's atomic theory. Now, a little bit later, right, as we move through a little bit of the experimental history, we have J.J. Thomson. And J.J. Thomson uses what are called cathode ray experiments, but really we don't need to know exactly how he get it, but J.J. Thomson identifies the electron as a small negative charge particle. So the key is this is smaller than an atom. So he identifies what becomes known as the electron as a particle that is smaller than an atom and is negatively charged. Now, what this spurs him to do is in 1904, he comes up with the plum pudding model of the atom, which essentially says that an atom is this sort of nebulous sphere of positive charge, which has these negatively charged electrons randomly dispersed within it. Now, why does the sphere have to be positive charge? Well, at this time, they already knew that atoms were neutral. in charge. Right? So a carbon atom, an iron atom, they weren't charged. So if electrons were negative, then there had to be positive charge to compensate for that. So that's why he says it's a sphere of positive charge. So again, there's a lot of work and experimentation going into understanding this idea, or more detail about the atom. So as a few more years pass, we get Rutherford, right? Rutherford, who not coincidentally is a student of J.J. Thomson, was conducting experiments to try to prove or support, I should say, the plum pudding model theory of the atom. And his most famous experiment in 1909 was what's become known as the gold foil experiment. And the key outcomes of this are the idea of the nucleus, and later on, in other experiments, Rutherford comes up with the idea of the proton, or positive charged particle in the nucleus. So his base experiment was, he took a sheet of gold foil, right, very thin, just a few atoms thick, and he directed what are known as alpha particles toward this sheet of gold. Now, a little background here to understand this is that Rutherford at the time had also been studying this new phenomenon of radioactivity, right? Now, we don't need to get into the details of radioactivity in this class, but when certain atoms decompose or undergo radioactive decay, they give off radioactive particles, right? One of those particles are alpha particles. So, an alpha particle, right, is a large positive charged particle. So large meaning it's about the same size as a helium atom, and it has a positive charge. So he has a radioactive element in here, and it's emitting these alpha particles, and he directs them at this sheet of gold. Right? And so basic theory went that because these alpha particles were so big compared to the electrons that were part of the plum pudding model, that they would pass directly through in a straight line because there was nothing large enough to stop them, right? And so he did the experiment multiple times, and what he observed was most of the particles did pass right through. But he did notice some of the particles were deflected a little bit. But even more surprising, a few of them were deflected at relatively large angles, meaning they hit something and bounced off of them. Now, after getting this result multiple times, he had to explain it. So, the way he explained it was to propose what we know as the nuclear model of the atom. So, in about 1910, he came up with the nuclear model of the atom, which is fairly close to what we know as the modern atom, and we'll talk a little bit more in detail about that in a few slides here. Now, just to kind of complete the cycle, the last subatomic particle that we think about was discovered in 1932 by Chadwick when he identified the presence of neutrons in the nucleus. So let's look a little more closely at Rutherford's results. So if we compare what would happen with the plum pudding model versus Rutherford's proposed nuclear model, we can see how it explains his results. So under the nuclear model, most of the atom's mass and all of its positive charge are contained in a small core called the nucleus. Right? And so the idea is that all of the atom's mass is in this very small portion of the atom. Right? And the nucleus is positively charged. Most of the volume, therefore, of the atom is simply empty space, which contains the negatively charged electrons that Thomson had identified in his plum pudding model. And so, by having this having this small, massive core at the center of the atom, Thomson can explain why a small percentage of the alpha particles bounced off of something, right? What they're hitting is they're hitting the nucleus, right? Something that is going to be more massive than the alpha particle, and they're going to cause it to bounce off. But only a few of them are going to do that because it's such a small portion of the atom. Now, to explain the ones that simply seem to graze or be deflected at relatively small angles, what he looks at is the charge, right? So alpha particles were positive charge. The nucleus is also positively charged. And one thing we know about charged particles, if they have the same charge, they repel each other. And so when these alpha particles get too close to the nucleus, they repel, and this causes some of them to move and shift by these relatively small angles that we see with some of the alpha particles. Whereas the majority of the alpha particles do simply pass right through because they're not hitting anything. So by invoking this idea of the nucleus and it's containing the positively charged particles, which he later identified as what we call protons, he can explain the behavior that he's observing. So this is a good example, right, of having a hypothesis, conducting an experiment. It does not support your hypothesis. So what does he do? He revises his hypothesis and then redoes the experiment or looks at the experimental results in light of the new hypothesis to see if they can explain his results. Right? Now, the last point to make here is that we know that the number of negatively charged electrons outside the nucleus must equal the number of positively charged protons inside the nucleus, so that the atom is electrically neutral. So an electron and a proton have the same charge but opposite each other. So the same magnitude of charge but opposite sign. So in a neutral atom, protons equal electrons. So we have the same number of protons as electrons. Now, as I said before, the nucleus is extremely dense, right? It contains about 99.9% of the mass, but occupies only a really, really small fraction of the volume, right? So it's very dense, very massive. Feature of the atom. And the electrons are distributed in a much larger region of relatively empty space and don't have much mass at all, right? Electrons are much less massive than protons, and the later identified neutrons that make up the rest of the mass in the nucleus. Now, we don't need to worry about the exact masses of these or even the exact charges of these. We use what are called relative masses and relative charges to work with these, right? And so we can see that in this small table if we look at it here, where what we see is that the proton and the neutron have essentially the same mass, but we don't really care what the exact mass in kilograms is, right? Here it is. What we care about is they essentially both have a mass of what we call 1 AMU. So AMU is a unit that was specifically developed so that we could easily compare the masses of these atoms or these subatomic particles. And so an electron, you can see, has a much smaller mass, right? About 0.0005 AMUs. So much, much smaller than either a proton or a neutron. And in terms of the charge, again, we don't need to know the actual charge of these particles. What we need to know is they're the same, but opposite charges. So to make it easier to deal with, we assign a proton as a positive 1 charge and an electron as a negative 1 charge. So same magnitude, opposite signs. And of course, a neutron is neutral and therefore has no charge. So we have our modern nuclear model of the atom where the protons and the neutrons make up the nucleus, right? The bulk of the mass of the atom. The nucleus is positively charged because of the protons, and the much smaller negatively charged electrons exist outside the nucleus and are held into that space because of attraction to the nucleus, right? We can't forget that these negatively charged electrons are going to be attracted to the positively charged protons in the nucleus. So the reason they don't just float away, right? Remember, there's no physical structure holding them in here, right? There's no walls like we think about in a cell, right? Is that attraction of the negatively charged electrons to the positively charged nucleus. Now that we have a basic understanding of the atom, we can start to think about elements, right? So elements are, the different fundamental forms of atoms, right? So in Dalton's idea, we know that different elements, right, have atoms that are fundamentally different from each other, but are the same within an element. So, elements are defined by the number of protons in the nucleus. Now, the number of protons is what we call the atomic number, right? So the atomic number, or Z, is the number of protons in the nucleus of an atom. And so an element has a given number of protons in the nucleus, and that's what makes it unique. So when Dalton's atomic theory, and he said that all atoms of the same element are the same, that has to do with the fact that they all have the same number of protons in their nucleus. And they're fundamentally different from the atoms of other elements because they have a different number of protons in their nucleus, right? So this is what defines an element. This is its unique factor, right? It's the number of protons that it has in its nucleus, or its atomic number. So the atomic number defines the atom as a given element. Now, while atoms can be identified by their atomic number, they are also represented by symbols, like what we call the chemical symbol, which is a 1 or 2 letter abbreviation for the element. These are all shown on the periodic table. So it's called the periodic table of elements for a reason, right? It contains a listing of all of the known elements, and they're listed by these chemical symbols, typically, these 1 or 2 letter abbreviations for the element. Now, some of these symbols make perfect sense, such as O for oxygen, but others do not make any sense at all, because while the symbols typically came from the original, usually Greek or Latin name for the element, the names have actually mostly been converted into English or some other, and so the symbols are still retained from those original Greek and Latin names, or sometimes other languages, and so they don't always match up with the name. So, for example, sodium, right, is Na, because the original name was natrium, right, and not sodium, right? And so sometimes the symbols can be a little confusing compared to the name, and this is why we have to put a little bit of effort into memorizing some of the name symbol combinations, and I'll talk about exactly which elements we need to do that with along the way. So that brings us to the periodic table, right? So the periodic table of elements lists all of the known elements according to their atomic numbers. So starts at atomic number 1 and goes through now atomic number 118 in terms of what elements are known. Now, I mentioned needing to memorize the names and symbols of certain elements, and these are the first 20 elements, in other words, hydrogen through calcium, right, 20, and a select other 10 elements, right? So we have Au, we have gold, we have silver, we have copper, we have bromine, we have iron, nickel, zinc, mercury, lead, and iodine. And the reason for choosing these particular 30 elements is that these are ones that are really commonly used in basic chemical compounds that we think about and chemical reactions. So the more that we can understand, be able to identify what they are, the easier it's going to be for us. Now, it's only the name and the symbol. Right? We don't need to memorize atomic numbers or memorize masses or anything like that, because those are told to us on the periodic table. But typically the periodic table will only have the symbol and not the name. So we need to be able to go back and forth. So now that we sort of understand what an element is and sort of why the elements are different and how we identify or label those elements, we can look a little bit more historically at how did we get to this periodic table. So you should have previously watched a video that discussed a little bit about the development of the periodic table. So I'm not going to spend a whole lot of time about that, but it was developed by Dmitri Mendeleev about 1869-1870 is when he published his periodic table. And the basic idea is that the elements are arranged originally in the original periodic table by mass, with certain sets of properties recurring periodically. This is called Mendeleev's periodic law. So what he observed was that when the elements were arranged by mass, he saw certain sets of properties recur every certain number of elements. So, for example, if you took lithium, he saw sodium, right, occur a certain number of elements later that had similar properties. And you go over a certain number of elements and you see potassium. And so what he did was that he took elements that had the same properties and put them into columns. Right? And these became the columns, or what we call the groups, on today's periodic table. So this set up a system of rows which give us the period, right? How often these things reoccur, and the columns, which give us these groups of elements that have similar properties. Now, the one major change that has taken place since Mendeleev's major original periodic table was that now, instead of being arranged by mass, they're arranged by atomic number or number of protons, which led to very few sort of differences. There's a couple of spots that elements flipped, but essentially, right, as we add protons, the mass is going to go up, so the order of mass is going to follow the order of protons. So modern periodic tables are arranged by atomic number. Now, of course, I guess the other change is we've added many elements since Mendeleev's periodic table, which at the time they knew about 60 elements, and as described in the video, right, Mendeleev actually predicted gaps in the periodic table, which were later filled in with elements as they were discovered. Now, the modern periodic table can be grouped in a bunch of different ways. We're going to talk about a couple of them. So, the first thing is we can define elements as either metals or non-metals, right? And so, metals occupy the left and center portion of the periodic table. They're defined here in sort of a tan color, right? And they make up the bulk of the elements on the periodic table. Now, metals have certain sets of properties. So just to name a few, right? Metals are good conductors of heat and electricity. They are what we call malleable and ductile, which means they can be formed into sheets and pulled into wires often. They tend to be shiny. But chemically speaking, one of the more important factors that will come up as we go through is that metals will tend to lose electrons when they undergo chemical changes or chemical reactions, right? And a little bit later, we'll talk about the idea of ions and how those are formed by losing or gaining electrons. Now, a much smaller number of elements fall under what we call nonmetals, and these are all grouped in the upper right-hand quadrant of the periodic table here in green. And these nonmetals have more varied properties, right? Whereas metals are all solids except for mercury, right? Nonmetals exist as solids, one liquid, bromine, and quite a few gases, right? And their properties, again, are more varied than metals. They tend to be poor conductors, unlike metals. And again, chemically speaking, nonmetals will tend to gain electrons when they undergo chemical reactions. So we have the vast majority of elements being metallic in nature, and a small set of elements grouped in the upper right-hand corner being nonmetals. Now, when you look at the periodic table, at least in certain forms, you may see identified a set of elements that sort of form the bridge between metals and nonmetals, right? These elements are sometimes grouped as what are called metalloids. And they are those elements that lie along the dividing line between metals and nonmetals. These might also be called semi-metals, and they display mixed properties, right? In other words, some of them are more metallic-like, some of them are more non-metallic-like, many of them have properties of a metal and properties of a nonmetal, depending on the specific property that we're looking with. You might have also heard these referred to as semiconductors because their conductivity, especially electroconductivity, is better than nonmetals, most of them, but not as good as actual metals. And furthermore, it can be controlled and changed based on the conditions. So these elements have become particularly useful in electronic manufacturing, in things like phones and computer chips and so forth. Some of the more well-known metalloids are silicon, arsenic, germanium, are some of the ones that most people have heard of. So we have these metals, nonmetals, and this small number of metalloids that lie along the dividing line between the two. So one way that we can divide it up is based on metallic nature. Now, another way we can divide it up is based on what type of element they are. And what I mean by that is, are they what we refer to as main group elements or what we refer to as a transition elements? So why do we have these two different categories? Well, the basic difference comes into is that main group elements, their properties are generally fairly predictable based on their position in the periodic table. So based on what column they're in, their properties are predictable. Right? And as we'll see as we go through, we can come up with trends or property trends as we travel through the main group elements. Now, on the other hand, transition elements, their properties are less predictable based on location, and we don't really tend to try to come up with trends, and they don't tend to follow the same trends as the main group elements do. So if we look at the periodic table, the main group elements are sometimes easily referred to as the tall parts of the periodic table. So they are the first two columns of the periodic table and the last 6 columns of the periodic table. So 8 columns give us the main group elements, whereas the transition elements are all of the other elements, are what we refer to as the middle elements on the periodic table. Now, in this particular picture, you might notice that we've left off what are called the lanthanides and actinides, which we'll come back to down here. They would also be part of the transition elements. So we have main group elements, we have transition elements. Now, particularly important for the main group elements is being able to identify the columns by what are called the group number. Right? And the group number is this number followed by an A at the top of the group. So the main group elements are numbered 1A, 2A, and then moving over to 3A through 8A, right? And so we can identify a main group element's location by its group number, right? So we can say that oxygen here is in group 6A, or sodium is in group 1A. Right? Now, we don't really worry about group numbers with the transition elements. We don't tend to try to identify them based on what group they're in. Again, we often use the group numbers as a way to think about the predictability of different properties. So we want to be able to identify or locate an element based on its group number. So if I tell you, what group is carbon in, you could tell me it's in group 4A. Now, furthermore, a few of these group numbers, or a few of these groups, have specific names that we associate with it that we need to know. So, besides knowing that they're part of the main group elements, and they're part of group 1A or 2A, there's specific names that go along with it. So group 1A, right, is known as the alkali metals. Group 2A is known as the alkaline earth metals. Now, I will make a special note, hydrogen is not part of the alkali metals. It is not really even part of group 1A, right? It doesn't have the same properties. It is definitely not a metal. It is typically drawn here for symmetry, probably. You'll even find some periodic tables where hydrogen is put over here. Essentially, hydrogen doesn't belong to any group in terms of its properties, but traditionally we place it on the top of group 1A, but it is not actually part of the alkali metals. So we have group 1A, the alkaline metals, group 2A, the alkaline earth metals. We have group 7A on the other end, which are called the halogens. And we have the last column, group 8A, which is called the noble gases. So these four particular groups, we want to be able to identify them by name as well as number. So if I ask you what group bromine is in, you want to be able to tell me it's group 7A, but you also want to be able to tell me bromine is a halogen. Now, beyond that, we have the transition metals as a group. The only other specific terms that we want to be able to identify on the periodic table in terms of groups is when we have these bottom part of the periodic table, these are known as the lanthanides and the actinides. So the first column, or the first row here, is called the lanthanides. And if you have trouble remembering which is which, if you look up right before this drop down, that right before the lanthanides is La, or lanthanum, and the actinides, the first element here is actinium, right? AC, right? So lanthanides and actinides. So we have four specific group names. We have transition metals, and we have the lanthanides and actinides. So some ways that we can navigate the periodic table. So this is going to take a little bit of practice, but as you go through this, we want to be able to learn how to easily move around and identify elements by their location in the periodic table. Whether are they part of the main groups of the transition metals? Are they in a specific group name, or group number? Does that group have a specific name associated with it, etc.? So that ends what I want to talk about in today's lecture. Next time we will continue on with chapter 4 and talk about some behaviors of atoms in terms of the formation of ions and other things associated with some of the with elements.